Hello everyone and welcome to this presentation. Today I, Jatin and my teammate Sarvesh Patki are here to present our IoT project for this quarter. We are working on an adaptive IoT communication system called SwiftNet. So to set the agenda for today's presentation, we are going over the motivation for this project, the current solutions, project goals, project approach, the hardware required, and at the end we are going to discuss the project outcomes and deliverables as well. Starting with the problem statement and the motivation for this project. In today's day and age, IoT is a major component of every system that we have, and most of those systems rely heavily on cloud-based applications. Cloud-based IoT systems often rely on communication going throughout the World Wide Web, and it suffers from high latency due to transmission delays. So we need a solution that operates efficiently within a local network. So what are the challenges that we'll face in this project? So our major challenge is reducing the round trip latency between two devices and the cloud. The second challenge we have is ensuring that we have a smooth communication system between the IoT devices on the local network. To provide an overview on the solution, we are going to implement a system where the most active sensor assumes the role of a master in the network, and that sensor is going to control all the devices and actions, selectively communicate with the cloud providers, and assume the role of all the actions. This is going to be real time, and we are going to provide a dashboard for the same, which can be observed by any end user. So the current solutions, as I mentioned earlier, rely heavily on cloud computing for data aggregation and analysis. They use protocols like MQTT and HTTP, which introduce latency due to internet dependency. Centralized control limits the adaptability and response time of all the sensors and the solutions. So the drawbacks of current solutions are one, high dependency on a stable internet connection, and second, the increased latency in the time-sensitive applications like industrial control. So SwiftNet offers multiple advantages in this solution. We use UDP for local data transmission, which offers significantly reduced latency. Overall, we have a master-slave architecture which allows a decentralized control model where the most active sensor dynamically manages the data flow. Cloud interactions are controlled by the master sensor, optimizing the cloud usage and the bandwidth.
Hello all, this is Sarvesh, and I'll be talking about the project goals, the approach, the hardware, and the deliverable. So the primary objectives are to create a UDP-based local network using master-slave architecture and integrate Raspberry Pi for data logging and visualization. The detailed goals are to reduce the latency and improve network efficiency. The master role selection, as in selecting a proper master according to the readings that we get. Visualization tools, so we'll be using Node-RED to visualize sensor data and master activity, and integration with the cloud communication. So the approach would be to use UDP communication, that is using microcontrollers to broadcast sensor data over the UDP network. Raspberry Pi listens for these broadcasts and logs the data. Selecting a proper master, so each ESP sends its sensor data to the others, and we would select accordingly the master with the highest rating. And the master role is to evaluate these ratings and also log them to the Raspberry Pi. And Raspberry Pi is basically acts as a cloud in this scenario. And also we'll be logging and storing all of our data on Raspberry Pi. And this data would be sent to the cloud or the Raspberry Pi in this case in specific intervals or according to some conditions if they're met. So we don't have to communicate with the cloud continuously. This is the hardware that we required for this project. That is the ESP8266 microcontrollers, Raspberry Pi, an LED board, which would be outputting our visualization for the data logging that we do on the Raspberry Pi, an LED matrix, 7-segment display, push button, photo registers, and shift registers. So this is the project outcome and deliverables. Low latency IoT system communications using UDP for local data exchange, a master-slave architecture for data flow and controlling cloud interactions, that how many times we are actually communicating with the cloud, a Node-RED for our visualizations, and the results, expected results for this project are to have enhanced response time for IoT applications due to reduced communication delays, optimized use of cloud services, only engaging when data needs to be offloaded, and improved system adaptability in the dynamic environments with varying sensor activity. Thank you for watching the presentation, and we are looking forward to working on this project during this quarter.